All right, let's start off with 3 exercises on indefinite integrals, and we'll have some on definite integrals later on. So for now, this would be a good time to pause the video because I'm going to go over the solutions to these 3 exercises. Alrighty, these are relatively quick ones. For our first integral, x to the power of 5, we can take advantage of the power rule here, and that becomes x to the power of 6 divided by 6. So we just add 1 to what we have in the power there and put that both in the exponent as well as in the denominator. Don't forget your plus c because there could be a constant that we don't know about. All right, for question 2, it's only slightly more complicated than question 1. For this one, we can take advantage of both the power rule and the constant product rule. So the constant product rule says that we can treat this constant separately, so we can leave it off to the side while we calculate the integral of x to the power of 5. So just as we did here, that becomes x to the power of 6 divided by 6. We can bring our 12 back into the picture, and don't forget your plus c. And you don't have to, but there's a nice opportunity to simplify things here. 12 divided by 6 is equal to 2 for a final answer of 2x to the power of 6 plus c. And then our last indefinite integral problem here, question 3, we can take advantage of the power rule, the constant product rule, and the sum rule all at once. So our first term here, this is the same as we had in question 2. So we know that this first term is going to come out to 2x to the power of 6. And then thanks to the sum rule, we can treat this second term separately. Well, negative x, that has a negative 1 in front effectively, which we can put off to the side thanks to the constant product rule. So we can just, consider the negative 1 out of the picture for the moment, perform integration on x, x to the power of 1, add 1 becomes x to the power of 2, and that 2 also goes into the denominator according to the power rule. We can bring our negative 1 back into the picture, which gives us the negative sign, and don't forget your plus c. That is your final answer to 3. All right, and then one exercise here for you to tackle a definite integral. So I recommend that you first try evaluating this expression using paper and pencil, and then separately, you can try using numerical integration in Python to calculate this definite integral as well. Knowing our rules, we can leave the constant 2 in front while we calculate the integral of x. Well, x to the power of 1 becomes x squared, and then we put a 2 underneath. So 2x squared divided by 2 plus c. We can simplify a bit here and cancel out the 2's, which leaves us with an indefinite integral of x squared plus c. And then now we can use that indefinite integral to evaluate at x equals 3 and x equals 4. So where x is equal to 3, this comes out to 3 squared plus c, which is 9 plus c. And at x equals 4, 4 squared plus c is equal to 16 plus c. And then our final step to calculate our definite integral is to take this term here, this expression here, and subtract this expression here from it. So our end point minus our starting point, and 16 minus 9 gives us 7. Positive c minus c is nothing, so our final answer is 7 squared units. And to evaluate this same question with Python code, you can use the same SciPy quad method that we already used once for numerical integration. Create a new function, 2x, and then pass that function, let's say we could call that function h, pass that into our quad method along with the start and end range that we would like to calculate our definite integral over. And that comes out to an answer of 7, which is the same as we got on the whiteboard. Okay, now that we know how to calculate definite integrals by hand, as well as using numeric differentiation in Python, let's finally wrap up these live lessons by calculating the area under the curve of the receiver operating characteristic curve that we already created earlier on.